Okay, so then let's move on to week 2 of the course. So now we'll do very basic management or interactions with geographic information. We'll read in data, write data to files using Geopandas. So we already know pandas data frames, so we'll get to know geodata frame data types. So that's the first part, and then there's the latter section about projections. So coordinate reference systems, which is quite fun. It can be a bit kind of challenging, especially at this time of the day, but yeah, I have some nice map tasks for you at the end of the lesson. So I would like to start this lesson actually by going back to the poll, just to kind of wake you up a bit. Just a second. So I have little kind of, just to check your background knowledge about these topics. So reading and writing files and projections. So as I mentioned last week, I'm assuming that you have taken some kind of GIS courses, and you should be a bit familiar with map projections and GIS file types and such. But maybe we can just kind of check our understanding. Let's go here. If you go to the poll page, and maybe in pairs, groups of 2 or 3 with your friend, try to define these concepts that are there. You can input your answer, and then we'll check them. So these are quite technical words or concepts: shapefile, geopackage, CRS, datum, and EPSG. And if you don't know, you can write, I have no idea, never heard this, or then if you know what is a shapefile, define it, give an example, what does it consist of, and so on. So then we'll be kind of playing around with these words throughout the lesson. So you can do it in pairs or alone if you feel like it. But maybe let's spend 5 minutes on this. Yeah, that was the last one. So I'll just kind of show where you can find, well, my definitions of these concepts. So shapefile, geopackage, CRS, datum, EPSG. So here you have a bit more text. If you disagree, we can discuss. But indeed, shapefiles is a vector data format, and it at least consists of .shp, .shx, and .dbf files. So at least 3 files, but then there's a bunch of other files you can have a look at in the Esri documentation. So for example, the .prj file contains the coordinate reference system information, and if that is missing, then you might be in trouble if you don't know what the coordinate reference system is. So I've been in situations when somebody sends me a shapefile as an email attachment, and then it didn't have the projection information, and then you just try to look at the coordinate numbers and figure out, and then it was some of these like old Helsinki projections or something. And then it's a bit risky just to define it if you don't know what it is. So geopackage, I would say it's the preferred format. And it's actually an SQLite database then packaged all in one file. Open source data format. Then indeed, coordinate reference systems define how then these coordinates in various systems relate to real locations. So we have some representation of objects on the Earth as points, lines, polygons, whatever. And then the CRS defines what does it mean if you have latitude, longitude, X and Y, something. So how does it then relate to an actual location on the Earth? Then with the help of, for example, a datum, so maybe the most concrete way to explain what is a datum, so you can have the same coordinates, but if you have a different datum, they can refer to a different location on the Earth. So for example, VGS 84 is a global datum, while then there are European level datums, Finnish datum, so it kind of attaches the coordinate reference system to some center point and kind of angle and scale on the Earth. And then indeed these EPSG codes, the name comes from European Petroleum Survey Group, who then were those who established this database, but basically the EPSG codes is a registry for these 4-digit or 4 or more digit numbers for different coordinate reference systems. So for example, 3067 is widely used in Finland, and then 4326 refers to VGS84, and at least these two I remember by heart because I use them all the time. Otherwise, you don't have to remember these. You can always go to the online documentation to check for the correct codes. Okay, so with these then we can continue working. And we'll now move on to seeing how we can actually read and write data. So I'm now on the page vector data in and out. We don't have to run these codes. I'll just kind of show what all we could do, and in this lesson we will focus on reading and writing shapefiles. So in Python, or when we are using the tools we are using in the background, there's a package called Fiona, which handles, for example, the reading and writing files. And then behind, or Fiona uses different drivers for reading different data formats. For example, SRI shapefiles or GeoPackages, or then a bunch of other file formats. And then if you're at some point wondering, you get some file in GeoJSON format, so you can run, there are these scripts you can run to see if Geopandas is able to read that data format. That's all you need to know about Fiona drivers at this point. So later on we will, for example, add KLM files to the list of files that it's possible to read. But you can see that there is, for example, SRI shape files are there, GeoPackage is there, GeoJSON, CSV files. So these common file types we can read in with Geopandas using Fiona without any additional hassle with the file formats. And this page contains examples of reading and writing data from different formats. So maybe later, if you get some data in a third format, you can come back to this page and see, for the example, this data doesn't actually now exist in our file system, but there's example for shapefile, GeoJSON, KML, GeoPackage, GeoDatabase. So GeoDatabase is the other kind of more modern SRI data type or database way of storing geographic information. Then you can read map info tabs. This is something that I use almost daily. So we have a PostGIS database, and then using this PsyCop2 package, you first make a connection to the database. There's some IP address for the host where it's located. If it's a local database, then this would be localhost. Port, PostGIS uses by default 5432 port. Then there's some database name, username, password. Then you would make some kind of SQL query to the database and get the data into a Pandas data frame. Then there's other ways of reading data from databases. You see that the script becomes a bit longer. So if you need these approaches, you can check the syntax more closely. Spatial light database. Then finally, web feature services. This is something we can try. It should work. So at least those of you who have taken the OpenGIS course should be familiar with web feature services. So for example, Statistics Finland offers data via a web feature service. so there's some host address, then there are some parameters, you need to know the table name and so forth. Then you make a request to that web feature service address, and then again, well, first you actually get the data as a JSON file, and then you convert that finally into a tabular format. So there's many tricks you can do, but indeed we'll be focusing on reading and writing shape files today. Okay, so at this point, introduction to Geopandas. You can start, if you already haven't started, the CSC Notebooks instance. I now haven't tested Binder, it should work. Let me know if you are for some reason using that. But let's now start a CSC Notebooks instance for everybody. I'll open mine. So you should now have under Notebooks, Lesson 2. There's quite a few notebooks. We won't go through in detail all of them, but the one we are starting with is Geopandas Basics. Should look like this. So I'll just check that everybody gets the system running, and we'll start looking at geodata frames. So we'll start now using Geopandas for interacting with spatial data layers. So Geopandas probably sounds familiar because we have been using pandas for working with tabular data. And in pandas we had the data structures, data frame and series. So in Geopandas we have geo data frame and geo series data types. And basically a pandas geodata frame, Geopandas geodata frame is a pandas data frame with geometries, quite logical. So here is an example, for example, of the data that we are using today. So there are some columns with regular attributes. There's the index value, and then there is a column that is named geometry. So that's important by default. The name has to be geometry so that Geopandas recognizes it. And then, as you can see, there are some shapely objects in that column. So those objects that we learned to create last week. So it's not more complicated than that. So this geometry column is actually then a geo series, and geo data frames and geo series have all the capabilities of pandas data structures plus some abilities for handling the geometries. So Geopandas is an extension for pandas. So as I briefly mentioned, Geopandas kind of works on top of other packages. Shapely we learned last week, and then there's, for example, Fiona that deals with the data inputs and outputs. Then there's at least PyProj, which handles the coordinate reference systems and so on. So GeoPackage is kind of this top-level tool for making, kind of bringing together all these a bit more complicated tools. Yes, I'll switch back to the notebook. How's it going in there? Yes, great. And how to import Geopandas to get all the functionalities. So import Geopandas as GPD, as we previously imported pandas as PD. So we can import Geopandas as GPD. Just check that works. Should run that. And if you want, you can add another cell if you type in GPD and press the tab. Dot and tab. I think you should get, yeah. So then you can find all the methods available in Geopandas. So instead of data frame, there's geodata frame. Then there's, for example, well, not so much different than some are different, some are then the same as with pandas functionalities. So in this lesson, before we have a little break, we'll read in some data, do some basic geometry calculations, write the data to file, and then do some groupings with the data to split it into multiple layers. And for this lesson, we have downloaded some input data from Python. So we have finished topographic database, or one piece of it from 2018. I'll just show it to you quickly on QGIS. So if you download data from Python, you get this kind of very deep file structure within which there's one square of data, and that's also split into multiple shapefiles. And here I have one layer, m_something_p. So it's all the polygon layers that belong to a terrain group in this data set. I could also add some base map just to show where we are. So at least those who have been around in the Helsinki region might recognize the region not far from Helsinki in there. So this layer we are then dealing with in this tutorial. And the layer we have selected contains indeed terrain objects. So this one shapefile, and within the terrain objects there are several feature classes. So there's different types of land use, including, for example, lakes, cemeteries, and so on and so on. And as a little task, our task would be to split this one shapefile into multiple shapefiles so that each class becomes one separate shapefile. So you could do that in QGIS by clicking and selecting and stuff, but that might take at least some while. So let's download the data. Just put this on widescreen. As we're now dealing with bigger data files, so we don't have them readily available, we need to open the terminal window for doing that. I'll just put it in here. Let me know if I need to drastically zoom in more. Zoom in a bit at least. Not that much. Sorry. Okay, so first navigate to the notebooks folder so that we get the file paths correctly. You can copy paste by shift and right click paste. And then again we use this wget utility to download the data. You can copy paste that as well, enter. You should see some action happening in there. Then you can press ls to list files in that directory, and you should see this l2_data.zip. Then unzip. Oops. File name, enter. You'll see quite many layers coming out as each shapefile has all these mini files coming with it. Then ls. You can also now you see that you have the zipped file and then the unzipped file in there. If I went fast, you can check from the web pages the syntax. So first wget download, then unzip, then you should have the data in there. You can of course also check from the file browser. There's the zipped file, unzipped file. There's some subfolders and then even some shapefiles in the root. Any problems with this? So the file we will be reading in is somewhere down here, one of these shapefiles. So this is the original folder structure from National Land Survey of Finland, as downloaded from Python. Okay, then before we get into action with the shapefiles, so I'll show you some tricks with file paths. I think we haven't yet done these. So in Python there's this very handy inbuilt module called OS. So I think it stands for operating system. You can import that. So as we now have this kind of a bit weird file structure, it might be nice to kind of somehow, in a clever way, define our input file paths. So for example, we could first define the folder, then the file name, and then only after that put those together. So you can actually paste, I think it's somewhere in here, sorry for scrolling up and down. Yep, I'll just close this one. So you have the file path, kind of the relational file path up there. You can just copy paste that because there's kind of room for typos in there. Paste that, and you can put the little R letter in front, so that meant that it reads the raw text in case there are some escape characters, so it doesn't break the string. Then we have the file name. And I also mentioned the file name somewhere up here. I think you can also type it in. Do we have it in here? Sorry. Well, I can just type it in here. So the file name that we will read in is called m_l413 to capital R underscore p.shape. It's the same as the folder name, basically, with the M and the P. So the M refers to the kind of terrain type, and then the P refers to the polygons. And then finally we would have the FP. So the OS package has a submodule called path. Then we can do ospath.join, then input folder and file name. You can quickly print that if you want to check. So this ospath.join can handle kind of folders and file names. So you can imagine if you would then iterate over all the shapefiles in the folder, you could then only change this file name piece of the whole thing. Okay. All right, I'll continue. Again, if you get lost behind, you can check from the web page is the correct syntax always. All right, so now we have imported Geopandas. We have a file paths to a shapefile, so we can read it in. As you remember, with pandas, we had this from CSV function. In Geopandas, we have this generic read file function that we use for reading all types of files. So gpd.read file is the function. We want to store the output in some variable, so I'll name that. And then now that we nicely handled the file path up here, we can just pass the FP parameter in there. Should go quite quickly, and then we can start checking the data. So we should have now a Geopandas geodata frame in our data variable in there, and furthermore can use all the familiar pandas functions for checking the data. Then I'll wait a while so everybody is with me. So gpd.read file path. So by default, Geopandas reads Esri shapefiles. If you're reading other types of data, you need to define which driver it should use. But with shapefiles, we can just pass a file name. You can type data.head. There's quite a lot of variables. Let's check which column names we have. Data.columns. So now that we have data from the Finnish administration, of course, all the column names are in Finnish. So I have provided here 2 lines of code to subset first by columns, only the columns that we're interested in. So there's the group column, class column, and then always remember to select also the geometry if you're subsetting geodata frames. Otherwise you kind of reduce it as a pandas data frame. Then there's a dictionary for renaming the columns. So ryhmä is group, luokka is class. So based on what you know, you should now be able to rename the columns. So do that, and then there's a little task for you to figure out how many rows, how many classes, and how many groups there are in the data. So let's spend a moment doing that. Okay. Okay, so then after that, at least you should be. We'll go through this in a bit, but try to figure this out yourself. Okay, I'll show the right answers here if you didn't yet finish. So how to figure out the number of rows in a data frame. For example, length. So len data. Let's test them one at a time. Take those out. So we have 4,311 rows of data in the shapefile. So in a way, quite a lot of data for a small area. Then number of classes. So if you checked the head, there's at least the first rows of data are from the same class. So it could be that we have only one class, but we don't know for sure. So you can, for example, check data, column class. Then there was this, there's this unique, but then there's this also, you could take length of unique values, but the shortcut is number of unique values, so unique. So there's 20 unique classes in this data set. So we will end up producing 20 shapefiles as we wanted to split the data by class. And then finally data group. The same thing, n unique. Oops. Comma. So there's only one group, so we have this terrain 1 group from National Land Survey of Finland, so the data was already split to different shapefiles per group, but not per class. Okay? So length gives the number of rows, and the number of unique values checks how many unique values are there in a specific column. Of course, when just exploring and getting to know our data, as we already did, it's always a good idea to open it in a GIS software if you have QGIS, but we can also do that in Python. So if we do data.plot in Geopandas, by default it plots the geometry. So we have this geometry column with the shapes, polygon shapes, and then data.plot plots those on the map. So this is not yet the visualization class, but just to kind of check that we have the correct data. And indeed, you might notice there's the Bodom Lake and other lakes at least visible. Then there's of course all these other classes, 20 different land use classes here from somewhere around Nuuksio in Espoo in this tile. So the data looks correct. It's always good to plot it so that you haven't mixed the x and y coordinates and so on. So then we can have a look at the geometries in Geopandas. Data column geometry dot head. So let's now just check the first values in this geo series. So as I mentioned, geodata frames need to have one column with geometries, and by default the name of that column needs to be geometry. You can also change the name of the geometry. Later on we'll, for example, calculate buffers in a new column and then redefine that as the geometry column. But if something is wrong, you can plot the data, then always first check that the geometry column is there and it's correctly named, and that your data type is geodata frame. Sometimes you might flip between data frames and geodata frames, and you have to redefine the data as a geodata frame and tell which column is the geometry column. And the values in this geometry column, I'll just copy that, paste it here. So if we would want to check the first value, we can use these indexers at, for example, first row, comma, oops, and then print that somewhere not on the map. So print the first value in the geometry column. So that's a polygon. We can, of course, double check that by checking the type of that object. Well, this didn't work. Never mind. Haven't maybe imported correct modules, but indeed there's a polygon object with 1, 2, 3, 4. This is quite a simple polygon, so it has four points in there. And then we can check the values on multiple columns, of course also with the head command, but just to refresh your memory on the iter rows, here I have already limited the iter rows to the first 5 rows, not to get too much stuff printed on the screen. Let's see. I'll just first jump back here. So now that we have this polygon object in that location, so then we can call all these shapely functions we learned last week. So for example, shapely object dot area returns the area in that coordinate reference system where the coordinates are. So then, if we want to check the area for many features, we can do it here. So under the comment, calculate the area. So now that we are iterating the rows, we always deal with one row of data, which is actually then a series of data. So we access from that row the column geometry and take the area, and then we can print can round it up a bit. Like this. And here, of course, maybe you can think further. We could then, if we have super big polygons, we could then convert them into square kilometers using the function we defined earlier, and so forth. Any questions? No? Yeah. We won't get rid of the iter rows and applying things on data frame rows. We'll be doing that also in this week's exercise. So repetition is the key here. We'll learn it at some point. But you'll notice that this iter rows is rather slow. We'll have some 80,000 points in the exercise, so we'll have to use some more efficient tools. Just as a side note. Okay, hopefully everybody got this. But indeed, often we can avoid using this iter-rows approach. The same thing we can kind of apply on all the rows at the same time. So now that we have these Geopandas objects, GeoSeries and geodata frames, so they actually have, so this is now our geodata frame, so it has an attribute called area. I'll just print the first values from there. So that's quite handy, one line of code. We don't have to deal with these shapely objects. Otherwise, if there is a geometry column, there are some objects that we can calculate the area for, then geodataframe.area should work. And we might want to add a column area to our data frame like this. So basically the data.area returns the GeoSeries, and then we insert that into the geodata frame. You can check that everything went well. So now our data frame has a new column area calculated based on the original geometries. And of course the area calculation depends on the coordinate reference system. Okay, this is good because here I hear if people are typing on the keyboards because they're so noisy. I hear no typing, so let's move on a bit. Okay, so based on this area field, we should be able to calculate some basic spatial statistics as we learned last week. So shapely object, just a basic floating point value maximum. Maybe you can calculate the minimum and mean. I'll just check that we haven't lost anybody. There are these specific kind of attributes that work on the geometric column. Not so, for example, area. Then there's bounds, some other related to the shape of objects that are stored in there. But if you have a pandas data frame and you do data frame.area, then you get an error because that doesn't exist for the data frames. Okay, so there's some very tiny polygon somewhere, some quite large, at least 4 square kilometers big. Might it be the Boodum Lake? I don't know. Can check that. So then again, we can use these basic data frame functionalities in here. Let's still see how we can write a shapefile, and maybe then quite soon we could have a little break, right? So let's first, before we automate the whole thing, so see how we can just write one class into a file. So first we need to select some data. Here we'll use the data.log that we learned in the GeoPython course, and we want to make a condition based on data.class. And if you check the documentation of this input data, you'll see that the value 36200 equals to lake water. So we'll put that as the condition. And run this maybe. What did I miss? Lock. Maybe just to refresh our memories, I'll just show this here. You don't have to repeat with me. If I do a condition based on one, so I have one column equals to one value. So this is a series where there's false, 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 false for those rows where this condition is not true, and then we can imagine that there are some rows where the condition is true, and then based on this true false series goes into the lock, and then lock selects those rows where the condition was true and then saves them into the output. So now if we check selection.head, there's values where there's only the class 36200 selected as a subset. So I'll move that where it was supposed to be in there. Of course, we can also check the selection in a bit differently before we save it into a file. We can plot it, so plot. So we were right, these should be the lakes in that area. So probably the biggest polygons in there. You can of course then, why not check the length of selection. So we will be writing 56 rows of data into file. So in Geopandas, there's again a simple function called toFile. By default, it writes shapefiles, so we don't need to do anything super fancy in there. I suggest that you would save the data in some folder. So now we are working in this kind of notebooks. Where are we? In the notebooks root folder under lesson 2. So it might be nice to save, not to have the shapefile in the root folder, because then we'll have all these little tiny files in there, and then you need to remove them one by one. So at least maybe to the root folder of the data, L2 data folder. So output folder equals L2 data as a string. And then output file path equals to, well, I'll do output file name. This is a bit different from the, so file name, what could it be? So we have class 36200.shp. You can rename it as maastotietakanta, lake water, whatever you like, but I'll do it like this. And then we have finally out fp, so the final file path would be os path join output folder output file name, like that. I'll check it out, fp pit. All right, so now we have a file path. Check. And then finally we'll do so geodata frame, so our selection dot to file out fp. And by default this to file writes sread shapefile. So if you want to write a geo package or something else, then you need to define a driver and maybe some layer names. But with shapefiles, this is enough. And you can then wait a bit. It should show up in the file browser on the left. I'll just go again there to the output folder. I need to restart my browser again. So there I have the shapefile with, there are these 3 mandatory files, and then there's the projection file because this layer actually had the projection defined. But we'll talk about projections after the break. Okay, so if you want, this is totally optional, you can then practice your skills and read in the shapefile that we just created back into Geopandas, but I suggest that we now take a break for 15 minutes, so let's continue 20 to 6-ish, so the cafeteria should be open, and if you had any troubles I can solve those in the meanwhile. Okay, let's continue then. There was a good question about these kind of attributes, checking the area from the geodata frame and so on. So Geopandas has rather good documentation. I recommend you to check it out. Just check that Yep, and Geopandas is currently being developed quite a lot. So if you're working on your own computer or for some reason have already installed Geopandas like a year ago, so do update it. If you check, for example, Geopandas data structure, so you see definitions of the geodata frame, points, lines, polygons, then geodata frames, geoseries, and then geodata frames below here. So, for example, then the attributes that are available are listed in here, so you can check the area, you can check the bounds, you can check the geometry type of the geodata frames based on this definition, and then of course, if we calculate some other columns, we can use all the attributes and methods from pandas as well. So this is rather good. It's not like often then if you check Geopandas documentation, you might have to go and read Fiona documentation or Shapely documentation to get more details, but this is quite an easy to read page. Okay, so we are now in lesson 2, Introduction to Geopandas, grouping the geodata frame section. So let's continue from there in our notebook. I actually forgot to restart my browser window. Let's see, let's hope this works. So final step, we have this layer from National Land Survey of Finland, and we want to split it into, what was it, 56 different or 20 different files. 20 different files based on the class column. So lakes into one shapefile, what was there, graveyards into one shapefile, and so on. So let's remind us about the data structure, data.head. So we have at the moment columns group, class, geometry, and area that we just calculated in there. And the column class is the one that we are now interested in. So data class, oops, and we can check the unique values in that column. Yes, so what do I have in here? Class. Need to restart my browser soon because it's getting slow. So there was maybe 20 something unique classes, which then represent different terrain types. We had them here at the top defined. So, for example, we have this 36200 lake water already. We saved that into a shapefile, so let's now do the rest. I'll scroll back down. There we are. So we'll use the group by method that you might remember from the GeoPython lessons and exercises. So we want to create a group, kind of create a mini data frame for each of these classes at once. So oftentimes I just name the group. If I group something, I call it grouped. Then data dot group by, and then by class. You can of course print this. Oops. Grouped object, but you'll see this representation of the data frame group by object. So it's the very same thing as we did with pandas data frames. There's the link to the lesson 6 materials if you want to have more information about that. And we can verify the keys, so by which we grouped the data, grouped groups dot keys. So these should be the same as the unique values in the column based on which we grouped the data by. So we have these, let's even check, well, we'll soon check how many groups we have. I think it's 20. But then we could further check how many rows of data each group has. So I think it was 56 rows of data for the lakes. But then what about the other groups? So here we'll write a quick for loop for key group in grouped. So for key is the key, so one of these 20 values. Group is a data frame, so the values for that group in this grouped object. I'll zoom that. And then we can print length of the group for each group. And maybe also we'll print the key, so some information in there. Key. Okay, so we see that class 32111 has 1 row. So there's some very tiny classes in there. 32421 has 110 rows, and you can check from the web pages what then these different class numbers were. And indeed, the 36200, which was lake water, has 56 rows of data. So we'll be generating shape files with the corresponding number of rows in each one of them. I can scroll back up in here if you missed that. Okido. Just to reiterate. So each of these groups is a geodata frame, as they have the geometry column in there, so they are subsets of the original data frame. You can also check. Now this group object is the last group in the data, so that class has eight rows of data, so we can even print the whole thing if we want. Like this. Okay. I'll move on to here. So finally, we will save the files. There's a little curiosity about naming output files in a flexible way. So we have learned before how to concatenate strings using the plus operator. So you have some string variable plus more characters plus string format of the key plus the file suffix. But then there's also different, maybe more elegant ways of kind of putting pieces of file paths or file names together. If we have, for example, a running number, you remember this base name exercise from GeoPython course. So you can use this percentage operator. So this percentage S is always then replaced by the corresponding value. Or then a new kind of more modern way is to use the format function. So you have a string with these kind of placeholders, and then again the first variable from here goes to the first location, and then the second one goes there. And the output from all of these three options is identical. So it would be terrain underscore 36200.shapefile. Just kind of to give you some options to format your string outputs when printing things. Okay, so in the next code cells there's some lines of code ready. So we define output folder, lesson 2 data. Then we even create a further folder. So now we'll be creating all of these shape files, all of which have 4 files. So it's kind of nice to put those in a separate folder. So this defines the name for a new folder that we'll create. Then the following file checks if the result folder doesn't exist. Create one. So you can just run this cell and then you should see the result folder under your lesson 2 data folder. There it is. So there's a new empty folder. If I would run this again, nothing happens because the folder exists already. So feel free to use this piece of script in your own codes. This is just a true and false statement, and if it's true, then a folder gets created using these OS functionalities that we imported previously. Okay, then the actual saving of the output files. So for each group, so for each class of terrain in this input data, we want to create an output file name. Output name. This is so slow. Equals, you can pick one of these formatting styles that's in the box above. I'll use this percentage operator. So I want to have some constant naming. Then with the only thing that would change is the class code. So here I only have one parameter for the string formatting. I need a space in between there. Works. We can add the information printing a bit after. Then we want an output file path. Now we have this results folder that we just created. And then inside the results folder, I want to then save the output, for each group, a file with the output name. And then finally, we want to, for the group, which is the kind of geodata frame, define the output path. You can run this. I'll just check that it works. So once you run it, you can go to the results folder and check what's in there. So you should have a bunch of shapefiles. It's nice when you're doing something like this to print, especially if it takes a while, you could print some information. So print saving file. Then we had this, maybe I'll put it underneath that one. Sorry. Just move it so I can use the out path. No, actually this was, you don't need to save it, I'm improvising unnecessarily. So there's a further, function in the OS module, which is OS path base name. So you can of course print the full file path, but for the user it's maybe enough to know the file name. So this OS path base name checks the file path, sees the structure, and removes all the folders and takes only the final file name from there. And then you get this kind of nice log information about your outputs. Okay. Any problems? Good. So now we learned how to read in a shapefile, write a shapefile, write multiple shapefiles, kind of automate a very simple file splitting process, and we on top of that calculated some areas based on the geometries. So there's already quite a lot of new stuff. There's this extra part underneath, save data to CSV. In the interest of time, I won't now type it in here. I'll just show it from the web pages. So as I have been saying here, we can do also all these tricks that we can do with pandas data frames. So if you would, we have this column area, you can take a sum from the grouped object for each group from the column area, take a sum, even round it up, so we get nice summary statistics of all these data. For example, like this. And then this is now, I think it's, you can check, I think it's pandas series at this point, which we can then save into CSV file, just as a tabular data, some further information about the shape files we have in there. So of course, often you save the spatial layers, and then you save some other type of attribute data just into regular text files using pandas functionalities. Great. Any questions so far?